So remember, for an ideal gas, the volume fraction is equals to the mole fraction, and that is equal to the pressure fraction, right? So if you have 18 liters of a gas and you know 0.32 volume percent of that is oxygen, you can calculate it 18 times 0.18 times 0.32. And that gives you the volume, which is 5.76 liters of oxygen. And from that, you can use Boyle's law to calculate the final volume, which is 1.15 meters cubed. Okay. The next part is determine the volume work of the compressor, the oxygen, determine the volume work of compressing the oxygen isothermally. How are you guys doing with that? Has anyone done it? Hands up, who's done it? Who's still doing it? Who doesn't want to do it? All right, I'll give you another 5 minutes and then go over that.
That's why
So determine the volume of work of compressing the oxygen isothermally. So remember, volume work in this case is PV, P2, V2 times log of P2 over P1. When you are isothermally compressing or expanding, always use the equation of states because it's in relation to volume. And the final one is sketch the process from part B in a PV diagram and justify the curvature. Would you like me to just show you the... Yeah? Can I get a hands of people who've tried it? And people who haven't tried it? Yeah? Okay. Anyway, so if you sketch that process, if you know the pressures, you can sketch it, right? You know you know P2, you know P1, and you know V1, you know V2. And the reasoning why it's curved like that, firstly, equilibrium always, it doesn't follow a straight path. But also the integral is the sine area. So the integral is the sine area on the curve. The integral is negative, and the integration is from the large to small, and the volume work is the negative of the integral. So because P1 is equals to PV equals P1 V1, and P equals P1 V over 1 V. So P is directly proportional to 1 over V. It's PV equals nRT, and it's either side. So you ignore temperature. Does that make sense? Not a clue? No?